In this video, we're going to talk about volume for the third and final time. So we're looking at solids of revolution again. Last time we talked about the disk or washer method to find the volume of solids of revolution. Sometimes that method is hard or even impossible to do depending on the functions involved. So in those examples there's a second method which might be better, and that's called cylindrical shells. And let me show you an example, see what that's all about. So let's say I want to find the volume of the solid obtained by rotating around the y-axis the region between this function, this is 2x squared minus x cubed, okay, it's a portion of that cubic polynomial, the region between that function and the x-axis, so this shaded part from x equals 0 to x equals 2, I want to rotate that around the y-axis. Okay, if I was going to do this with washers, or well, it would be washers, I would have to take my cross sections perpendicular to the y-axis because I'm rotating around the y-axis. So my cross sections would look like a little line segment here at some given y. Let's say y was 0.8. You take the little line segment here at y equals 0.8. You'd rotate that around the y-axis and you'd get a washer. Some issues there. One, the inner and outer radius are given by this same function. So last time we had two different functions going on, but here the inner radius is given by this function. The outer radius is given by that same function. So we'd have to get both of them from the same function. And also to do that we need to figure out what is x in terms of y. So we'd have to solve this thing for x. So put y here in place of f of x and then solve for x, which is possible. This is a cubic. There's a cubic formula similar to the quadratic formula, and it would give you as many as 3 answers, and we want 2 of them, one for this inside, one for the outside. That would be difficult but not impossible for this one. Another issue is, what are the limits of integration? We can see that this region starts at y equals 0. Where does it stop? It stops at whatever the maximum is. So we'd have to figure out the maximum y value. Now for this problem that wouldn't be that bad. We just, we need to take the derivative, find out where the derivative is 0. You could find this local max. But more work than we had to do with any of the examples we had last time. And so there's a different kind of approach here. Let's look at the 3D picture. Now again, I'm not going to manipulate this because my computer will freak out, but you can click and drag and rotate it around and look at it from different angles if you want to. It's kind of like a bundt cake. And so the idea with cylindrical shells is instead of taking a cross section this way and getting a washer, instead we're going to cut this bundt cake with a cylindrical cookie cutter type of thing. So take a big cylinder and press it down here and make kind of a slice. Instead of slicing horizontally, we're going to press down this cylinder vertically. And I found a picture on the internet of somebody who drew this and actually did it with an actual kind of cake looking thing. So here's our solid of revolution. Okay, so in this person's picture they're rotating this region here around the y-axis, so we get a bundt cake type of thing. Here's the actual jelly ring, they said. Instead of taking a line segment here this way, a horizontal line segment, and rotating around the y-axis and getting a washer, instead we're going to take this vertical line segment. And you rotate this vertical line segment around the y-axis, what you get is not a washer, you get a cylinder, or a cylindrical shell. It's the side of the cylinder. It doesn't have the top and the bottom, it's just the side. Okay, so imagine taking this little line segment and rotating it around. Hold up your finger and rotate it around an axis, and you will trace out a little cylindrical shell. Okay, so that's what we're going to do. That's the idea. So we'll take a kind of a cookie cutter, press it down to make a cylinder, a big one, and we'll take a second one a little bit smaller. So we'll get a slab. Okay, so here's the outer one. You can kind of see this outer cylinder, and then there's a second one close to it inside, a little bit smaller radius cylinder. Okay, so you got these two cylindrical cookie cutters. They're both about the same size. One is slightly bigger. You press that down, and what you get is this little sliver of cake going around. And here's what we have with this guy's jelly ring. Here's the little r, the inside radius. It's not marked the outside radius. Big R would go out here to the outside. Okay, so you get this little, almost a cylinder type of thing. Now it's not exactly a cylinder because you can see there's some curve to the top of this because the function is not a constant. There's a slope there. But that's the idea. We got this thing that has kind of a cylinder-like thing. So how are we going to find the volume of this thing? Well, what we're going to do is take our knife and we're going to cut right here and open this slab up, unroll it, lay it flat. And when you lay it flat, you have something that's almost like a rectangular box type of slab. So what's the volume of that slab of cake we get when we lay it flat? Well, it's almost length times width times height, treating it as if that slab is like a rectangular box. So the height of this cake is given by, here's the height, it's given by the function. So the inside radius I called little r, the outside radius I called big R. They're about the same. F of big R and F of little r are about the same as long as little r and big R are pretty close together. So that's roughly the height. Now the height's not actually a constant. That's why I have an approximation here, so because there's a little slope. The circumference of this cylinder gives you the width of the slab. So if you cut this and lay it out flat, how wide is it? Its width is how far it goes around. That's circumference, which is roughly 2 pi big R or 2 pi little r. Those are about the same. So the width is a little bit different on the outside versus the inside. So this is not exactly a rectangular box, but roughly. The thickness, which is kind of the height of this slab as it's laying down, is the difference between the inner and outer radii. So I have approximations because our cylindrical shell is not exactly flat on top. That's this approximation. And this approximation is also there. Even if the function were not curved, even if the function were totally flat, you'd still have this approximation here. Okay, so what's the volume of that slab? That's the volume of this shell here. It's roughly the height times the width times the height, or thickness. So this is an approximation, and of course we're going to do this many times. We're going to cut this cake up into a bunch of slabs, use the same formula to approximate the volume of each of the slabs, add them up, and get an approximate volume for the whole cake. And then we're going to make the approximation better by making those slabs thinner. So we're going to make big R and little r closer together. So these approximations get better and better. And when you take the limit as the number of shells goes to infinity, or as this distance between them goes to 0, you get the right answer, the volume. And it turns out that that whole process gives us a Riemann sum, and so that limits an integral. So in this particular example, that I skip over this one. This example we're doing up here, the bundt cake for this thing. All right, so this is our function. That gives us the height. And the radius comes from x. Okay, x, see here, the radius is the x value. That's the radius of our shell. So r is x, and difference of the r's is delta x. So this is f of x, 2 pi x, delta x. Take the limit as delta x goes to 0, and you get delta x becomes dx, and then we got f of x and 2 pi x. I changed the order a little bit, just, I don't know, because I felt like it, I guess. So in my particular example, the x values range from 0 to 2, and so we got 2 pi times the radius, that's the circumference, and then f of x is the height, and then dx is sort of like the thickness. Okay, and there's the answer. I did it in Sage, 16 pi over 5. That's the volume of that little bundt cake thing. So in general, if you have, if you're rotating around the y-axis, the region that's between the curve, y equals f of x, and the x-axis, I'm going to assume here that the function is positive. Don't want to worry about crossing the x-axis and dealing with negative function values. Let's just have positive function. I'm going to rotate the region between that function and the x-axis around the y-axis. And here's our formula in general. It's 2 pi x times f of x, integrating from wherever the x values are. X goes from a to b here. Or in other words, 2 pi times the radius of the shell times the height of the shell. And the reason I put it in this format is because we're going to have we're going to rotate around other axes. So instead of the y-axis, we might rotate around another vertical line. And in that case, you're not going to have, the radius is not going to be x. The radius will be something else. We'll show examples of that. But this is the general idea. 2 pi times the radius of your shell times the height of your shell. Okay, here's another example. I'm going to look at the region under the square root of x, so that's my function. Here's my shaded region from x equals 0 to x equals 4. I'm going to rotate that around the y-axis again. Okay, so the volume is, I integrate in the x direction from 0 to 4. I have 2 pi times the radius of my shell. The radius is given by x value because I'm rotating around the y-axis. So it's the distance from the axis of rotation to wherever I'm going to cut my shell. So that's x. The height of the shell is given by this function, square root of x. Now it is possible to do this one with washers. It wouldn't be that bad. We'd have to rewrite this as x equals y squared, and we'd integrate from y equals 0 to y equals 2 of the pi times y squared squared dy. We could have done that. That would have given us the same answer. So anyway, it's just an example. Here's the 3D picture, which again I'm not going to manipulate. This blue part is like the top, and you need to imagine this is all, the green part's all filled in. So the solid is kind of between this green boundary into the blue. So it's this part under here. Don't fill in this part on top. Alright, what if you rotate around a vertical line other than the y-axis? Let's do an example of that. So here I have this function, this guy. I want the region between that and the x-axis from x equals 2 to x equals 4. So this is a region, this is positive, so we're above the x-axis here. But I'm not going to rotate around the y-axis. Instead, I'm going to rotate it around the line x equals 6. So this is my axis of rotation. So we're taking this thing and rotating around there. This is going to give us a bundt cake looking thing again. But I need my integral to be 2 pi times the shell radius times the shell height. Now the shell height is given by the function, that's f of x. So here's 2 pi. The shell radius now is not given by x. X is the distance from the y-axis to wherever I'm taking my shell. I don't want to do that because I'm not rotating around the y-axis. That's not the center. The center is here at 6. So the radius is the distance from this axis to whatever x value I cut my shell at. So in other words, 6 minus x. So 2 pi, 6 minus x is the radius, f of x is the height, x goes from 2 to 4, and Sage tells me the answer is 8 pi. Here's the picture of that one, if you want to play around with that one. Okay, so far I've only done rotation around a vertical line. What happens if you rotate around a horizontal line? Well, in this case, we're going to do everything in the y direction. So we're going to have a y integral. Our limits of integration are going to be y values, and we're going to have y functions. Okay, so here's the region I'm rotating. I got two functions. The one on top is 2 square root of x plus 1. The one on the bottom is the line x plus 1. I want the region between them as x goes from 0 to 4. Okay, so here's my region. I'm rotating that around the x-axis. Okay, so we could do this with washers, and it probably be easier with washers. But just as an example of rotating around a horizontal line, let's try it with shells. So our shell radius is going to be y. Okay, to get a cylindrical shell, I need to take a line segment this direction. Say at y equals 3, I have to go this direction. I rotate that around the x-axis, and I get a cylindrical shell. So the radius of the shell goes from the x-axis up to whatever y value I have. So the shell radius is y. So we're going to have 2 pi times y, and now I need the shell height. The shell height is not given by either one of these functions. It's given by the difference between them, the horizontal distance here. So if I take y equals 3 as my radius, the height is given by the difference between this value and this value. Well, this one minus this one. The bigger minus the smaller. So I need the x value here. For this line, I need to subtract the x value here, and that will give me the height of my cylindrical shell. So in order to get the x values for these, I need to solve my original function. So they're given y in terms of x. I need to solve these for x. So the first one, I get x is y minus 1 quantity squared divided by 4. In the second function, I get x is y minus 1. So the height of the shell is the x value from the one that's bigger, further to the right, In that case, it's the line. The line is the bigger one. So I take the line and I subtract the parabola. So the volume is 2 pi times the radius of the shell, which is y, times the height of the shell, which is the difference between these two functions. And y, the limits of integration, it goes from 1 to 5, you can kind of see from the graph, or the original problem gave you the x values, 0 to 4. You can plug those into this function. So this function, when x is 0, y is 1, whether you put it, whichever one you put it in. When x is 4, right, you put it in here, you get square root of 4 is 2, 2 times 2 is 4, plus 1 is 5, or 4 plus 1 is 5. So it's 1 on one side, 5 on the other. There's no gap between these two functions. Make sure you change these limits of integration though to y values. Okay, don't use the x is 0 and y is the x is 0, x is 4. That's not the right limits of integration. Okay, so here's the picture. Again, you got to think of sort of the green jello that's sitting on top this solid blue thing. It's the green part that's the solid. This inside part is empty. Alright, what if there's a gap between the functions? Okay, so here I have the parabola y equals x squared. That's the bottom. And then I have the line 2x plus 4, which is the top here. I want the region between those, so there's a gap there. I'm going to rotate this around the x-axis. Okay, so to use cylindrical shells for this thing, since I'm rotating around the x-axis, right, x-axis, yeah, my shell radius is going to be given by y, but the shell height depends on where I am in this picture. Okay, so if I say y is 2, for example, and I take a little horizontal line segment there, and I rotate that around the x-axis, I get a cylindrical shell. The radius of that would be 2. What's the height? The height is this distance from the y-axis until you get here, the x value on the parabola, which is, solve this for x. X is the square root of y. So this is the square root of y, would give me this height. Now when I get up here past 4, say y equals 5, the radius would be the y value, 5. The height now is not given by this parabola, it's given by the difference between 2, x is 2 here, and minus the x value here, which you'd have to solve this equation, y minus 4, divide both sides by 2. The height formula changes once you reach 4. So from 0 to 4, the height is one thing, it's given by the parabola, and from 4 until 8, it's given by the 2 minus the line. Okay, so did I say all these things? From 0 to y is 0 to 4. Okay, you got to do two different integrals. That's the moral of this story. From 0 to 4, it's 2 pi times the radius, which is y, times the height, which is given by the parabola in terms of y. So square root of y is the parabola. And then from 4 to 8, you have a different formula. It's 2 pi times the radius. The radius is still y, but the height is now 2 minus the line. The line is y minus 4, all divided by 2, or if you kind of break it up into two fractions, half y minus 2, whichever way you like it. Don't forget these parentheses here, though, and these parentheses here. Those parentheses are important. These first set of parentheses, because I need to multiply this entire difference by that, so make sure your multiplication works right. This set of parentheses, make sure the subtraction works right. I need to subtract the entire line, not just the first part. So parentheses important here. Alright, now of course you could have done this one with washers, and again with washers probably be easier here. Rotating around the x-axis to do washers, we'd take a vertical line segment and you rotate that around the x-axis, you get a washer. The outer radius of the washer given by the top function, the inner radius given by the bottom function. It'd be simpler that way with washers. So cylindrical shells is not always easier. You had a choice now. Figure out which one is better. Sometimes washers is better. Sometimes shells are better. It depends on which axis you're going around and what kind of functions you're dealing with. In many examples you could do both. One might be harder than the other. But this last picture of that, I don't know, it doesn't look quite right to me. You can twist it around and see what you think. Again, this inside part, the blue part's not filled in. It's the greens that's all filled in between this outer of the green and the blue. Okay, so that's our last look at volume, and next week we'll move on to another application of integrals.